Welcome back to Boolean Maths. So today we're going to be graphing some rational functions. We have 3 examples that I'm going to do. The first one, not really a rational function. It presents as a rational function, but once it reduces, you're going to see that it's not. And then the other 2 are common rational functions. I'm going to try to make this video as quickly as possible. You're always welcome to speed through if you understand what we're doing. I do intend to be as thorough as possible so that if you are new to this or just need further explanation, you can watch it at your own pace. Okay, so let's get started. So first example. Looks like a relatively intimidating problem, right? It's got the ratio of 2 polynomials. So I've provided a list of steps for us to follow that just kind of help us to establish all of the necessary elements for a rational function. And if you looked at some of the previous videos, you now know how to establish end behavior asymptotes. We know how to find holes or vertical asymptotes, x-intercepts, y-intercepts, yada yada. Okay, so if you follow these steps, everything should go well. First thing they want us to do is they want us to factor both the numerator and the denominator, and just so we have everything in factored form, if possible. So we're going to take a look at this numerator here. We've got 2x and x, and then 15 is prime. It's not prime, but it factors into 3 and 15. So we only have a couple options here. I really need to get 1 in the middle for the b term. So probably the 5 goes here and the 3 here. We need positive 6, negative 5, perfect, all over x plus 3. Great. So when we look over here now, they want us, so now that we have it in factored form, I guess we could record that over here, try to do it neatly. G of x equals 2x minus 5 times x plus 3 over x plus 3. Cool. And then they want us to state the domain. It's going to be all x such that, or all real numbers such that x cannot be negative 3. All right, well, then they want us to simplify, and you can see that it does. Simplifies right here. Those 2 cancel out. So I'm going to write the new g of x is equal to 2x minus 5. That doesn't look so intimidating anymore. It's just the equation of a line. However, that's the equation of a line with a restriction on the domain. There are no vertical asymptotes here, so there's only one other option. That's the value negative 3. X cannot be negative 3, so we need to acknowledge that. And I usually recommend doing that immediately after you divide out any factors. The second you eliminate those 2, you should come over to the domain and annotate right on the domain, this element that's undefined is not a vertical asymptote. Just say what it is. It's a hole. Vertical asymptotes are standard, so you don't have to say, oh, and this one's a vertical asymptote, this one's a hole. I usually just notate the holes because they're kind of unique. So I'd say I have a hole at negative 3, comma, and then we need to evaluate g of negative 3. So let's plug it in. So g of negative 3 is going to equal 2 times negative 3 minus 5, which equals, it's negative 6, negative 11. Okay, so at negative 3 comma negative 11, we have a hole. Now, from this point on, locating x-intercepts, y-intercepts, vertical asymptotes, all of that other stuff, I mean, the x-intercept, sure, we can find. X-intercept is always just taking our function and setting it equal to 0. So we know that x is going to equal 5 halves. So x-intercept is going to be at 2.5 comma 0. Y-intercept, just plug in 0 for x, that's negative 5, or 0 comma negative 5. All right. No vertical asymptotes, no horizontal. Don't worry about step 7. Nope. So graph by hand. Wonderful. So what I'm going to do is I just have these fairly generic axes over here. yeah, let's just go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8. Okay. I was going to use regular graph paper, or just a regular, more perfect graph. But yeah, to be honest, the -11 went off. I had it only going up to -10. So I just figured, you know what, let's just sketch this. So we can graph the point, actually, -3, -11, right? -3, -11 would go, here's -3, right over here. And another point that's on the graph is positive 2.5. I don't even need to use the slope here. I'm just going to use that that other value. And then we have 1, 2, 3, 4, 5. Yeah, this is not perfectly drawn to scale, obviously. So I'm just going to go for this, and we'll draw a line that goes through those. And yeah. That's pretty good. So we'll take that line. I just need you to use your imagination. It's pretend time. And I want you to imagine that the y-intercept is also, this is -5 here. Wow, we're having a rough time. This is -5. This is our hole at -3, -11 over here. And you don't have to label the x-intercept, but the main thing is that you see that the hole, let's see if I can grab that. Nope, I can't. Okay, it's fine. The hole is just a point that's been removed from our line. Okay, and that's it. So that's a perfect case in point of what a hole would represent. It's just an undefined element in the domain that really shouldn't be undefined, but it is because the function as it was presented was not simplified. So you had to state the things that were not permitted, the values that were not permitted. And then upon simplification, you really have a nice continuous function, but you do have to go over to the value at -3, which is -11, remove that point, and just put a little open circle there. Okay, moving on. So these are slightly more difficult, or more tedious, let's just say. And yeah. All right, so let's do that first step again. We're going to factor the numerator and denominator. It looks like the numerator is in good shape. X plus 3. Denominator, x, 3, 2, plus and minus. I believe that is correct. X squared, and then we have 3x positive minus 2x, and we have x, and then the product is -6. Great. So once again, looks like this will reduce, but first I'm going to state that domain. So the domain is going to be all x such that x cannot be -3 and 2. And we can just move this over here. So we have f of x in factored form there. Great. And now we can reduce this down. So the new f of x equals 1 over x minus 2. This just got a lot easier. Some of you might recognize this as the function 1 over x shifted to the right 2 units. So we sort of have an idea for what this should look like, but it's still a rational function, and we're going to treat it like it is. So let's do this. So now what you might notice is that since that x plus 3 factor was divided out, once again, I'm going to just put a little ring around that and note that we have a hole at -3, comma, and in this case it's f of -3. That's sort of funny. I think the last one was also at -3, right? That's just an interesting coincidence. All holes don't happen at x equals -3. All right, so this is equal to 1 over -3 minus 2. It's -5. So -1/5. So that's technically part of your graph. It's a not part of your graph. So you just graph it like you normally would. Just don't forget to put that hole there. You could actually use the whole as a point because it kind of goes up to one side and it comes out the other. All right, so any remaining undefined elements will be our vertical asymptotes. So let's state the x and y intercepts. So the x-intercept, that comes out of the numerator. There is no x-intercept because there's nothing that will make this function 0, right? The only thing that could make a fraction equal to 0 is if the numerator is equal to 0. In this case, the numerator can't equal 0 because there's no variable there. So x-intercepts, x-int, not applicable. Y-intercept, you just plug in 0 for x, so that's f of 0, and that's going to be at -1/2. So as I'm going along, I guess it's worth putting some of this stuff on here, right? So let's go to the y-intercept is going to be at -1/2, so let's put it there. I guess we'll graph it in red. It's more visible that way. So -1/2 for the y-intercept. We have a hole at -3, -1/5. 1, 2, 3, and -1/5. I'm just going to say that's going to be about right here. Great. And then, all right, so those are our attributes so far. And now we need to put in our vertical asymptote. There's a vertical asymptote at x equals 2. Horizontal asymptote, this function's proper, right? So we know that it's y equals 0 is our horizontal asymptote. So let's put those in. So horizontal asymptote, I'll use a nice green line. Just going to draw a horizontal line and move it. Whoops. So that's our horizontal asymptote, and then our vertical asymptote. Again, I'll just draw a vertical line. We'll move it to where it needs to go. That's going to be at x equals 2. Right there. Cool. So these solid green lines, normally use dotted lines. I haven't figured out. Maybe there's a way to just automatically make these dotted in this program. They say determine points, if any, at which the graph intersects the horizontal or oblique asymptote. Well, the horizontal asymptote is y equals 0. So if I wanted to know, does my function 1 over x minus 2 ever equal 0? We know that that's never, because in this case, the horizontal asymptote is our x-axis. So when we were looking for x-intercepts, we could have found that. So that does raise an interesting point that a lot of you learned that or misunderstood that an asymptote can never be crossed. Only vertical asymptotes can't be crossed by your graph. Your horizontal or oblique, those are end behavior models. That's just what your graph looks like from far away. That doesn't mean that the actual function doesn't cross it at some point. Typically, a horizontal asymptote, the graph will, if this is your asymptote, the graph will come in and just get really, really close to it. But it's possible that the graph could have crossed it at some point, come up, and then come back down again. So why would I care about it crossing, or why would you care about it crossing, your graph crossing the end behavior model or the horizontal asymptote or oblique asymptote? It's because it's the horizontal asymptote is a boundary, and like the x-axis, it's once you've crossed it, if you know it's the only time you've crossed it and you're on one side of it, then you're never going to have to cross it again, so you sort of know where you are. So it's just worth checking. It's nice to know if that happens, but in this case it doesn't. So once we're on one side of that asymptote, we're going to stay there. All right. Graph the intercepts and the asymptotes. Did it. Compute one function point between x-intercept and the asymptote. Okay. Well, we don't have any x-intercepts here, and it probably wouldn't be a bad idea to plug in a value or two just to give us some accuracy when we graph this. So I think I'll do that. Let's plug in a value to the right and to the left of this vertical asymptote over here. So a value to the left would be 1, and a value to the right is 3. So let's just go ahead and evaluate f of 1. That's going to equal negative sort of 1 over 1 minus 2 equals negative 1. So we know we have a point right there. And then when we do f of 3, that's going to equal 1 over 3 minus 2, which equals, also this one equals positive 1. Great. Let's get these guys out of the way. And then the rest is just graphed by hand. All right. So I know that because these green asymptotes, a vertical asymptote doesn't get crossed, and we also know that the horizontal asymptote is not going to get crossed either. We know that one part of the graph is in this region and the other part is in this region here, right? So I probably could have put a couple more points in, but again, this is just a sketch, and it's a very shaky sketch. If you don't mind, I'm going to try that one more time. I'm just going to put it on my tabletop here. And I tend to snuggle up to the asymptotes a little bit too quickly. And I love my technology, but I have to say it's graphing on a piece of paper is a little bit nicer. Okay. I can't believe I just said that out loud. All right. And and it goes through that hole, whoops, here, and then pretty dramatically it just drops down like that. Again, it's kind of shaky, but you have to also appreciate that, again, this is just a sketch, so it should look something like that. Here, let me line this up for a sec, and cool. So one thing that I like to do, and it'd be really cool if this already exists, you can let me know in the comments, but it'd be really cool if there was a graphing app that, like Desmos, if they added a layer for like an iPad or a tablet where you can turn the graph off and then try to graph it yourself and then turn it on again. So what I've done here is I have, through the magic of editing, I actually did this graph in Desmos. I'm using Desmos, the graphing screen. So I'm going to just go, all right. So hopefully that worked out. So if you look, I mean, you can see that I did a pretty decent job. I mean, the Desmos one is the little red one underneath it. All my key points pretty much line up. I mean, estimating 1/5 right here. It's off by a little bit. Notice how Desmos doesn't put a hole there. It's like almost impossible because there's so many points. There's infinitely many points just being stitched together there. So to just acknowledge that one and put a big hole there, I mean, it would be nice if they did that. I guess we'd all know what it meant. So anyway, yeah. You see how I was off by a little bit with the curvature on that. I mean, both of my key points that I plotted there, they're spot on with what Desmos came up with. Anyway, so that was just, probably more information than we needed for that. I'm going to do the same thing with the next problem. So actually, speaking of the next problem, let's just finish this up. One more. All right. Factor numerator denominator, and let's get rolling. So we're going to have x times x squared plus 8x plus 15 over, I'm going to start factoring the bottom since it doesn't need anything else factored there, 5, 1 plus minus, and then we're going to factor that other quadratic. So we have x, 5, 3, plus and plus. Looks pretty good. And once again, we have another whole scenario. So I'm just gonna take this one and copy it, just bring it over here. Okay. So this is again, f of x equals, that's our factored portion. State the domain. We have all real numbers such that x cannot be -5 and it cannot be 1. I see that these two are going to divide out now. So I can restate my function. I'm going to actually leave it in green. F of x equals x times x plus 3 over x minus 1. So as I mentioned earlier, immediately we need to go over that negative 5 and acknowledge that we have a hole at negative 5, comma, and then we have to do f of negative 5 right above there. And f of negative 5 is going to be negative 5 times negative 5 plus 3 is negative 2 over negative 5 and then minus 1. So we have positive 10 over negative 6, which works out to be negative 5 thirds. So I'm going to write that as a mixed number because I want to know where that is. So it's going to be 1 and negative 1 and 2 thirds. So I know I have a hole there. So at negative 1 and 2 thirds, sorry, at negative 5, negative 1 and 2 thirds. So negative 5, negative 1, and it's probably about right there. Why not state that hole? Okay. X-intercepts, that's where the numerator is going to be equal to 0. So we have x-int at, and I'm just going to list them, negative 3 and 0 as a set, because now there's more than one, why write them as coordinates? And the y-intercept, that's just going to be at whenever x is equal to 0. So it's the origin. Yay. Okay, so let's put that y-intercept and an x-intercept right in their place, 0. And the other x-intercepts at negative 3. 1, 2, 3. Interesting. Vertical asymptotes. We have one vertical asymptote at x equals 1. And horizontal asymptote. Now that's an interesting one, right? Because we have the opportunity here to long divide because the numerator is 1 degree higher than the denominator. So we're actually not going to have a horizontal asymptote. We're going to have what's called an oblique asymptote. So we'll do that in a moment. But yes, that'll be fun. X equals 1, we need to put that asymptote in. And once again, I will just draw a green vertical line. Let's try to draw that straight. And I'll put it in its spot. Okay. So that's our vertical asymptote. And okay, so you have the option when you go to long divide here, you could long divide into, and I would recommend doing this, into the simplified. So now long dividing into the simplified would require that we just rewrite this over here as, let's just distribute that term in the numerator. It's going to be x squared plus 3x over x minus 1. And let's just note that that's just for long division. Okay, so I'm going to just take that and long divide over here. So we're going to find that asymptote. Really not a big deal if you just went right back to the original as well. I just, less is more. So this will be a lot faster if we just try to long divide x minus 1 into x squared plus 3x. May as well put the 0 placeholder there just for giggles. The other thing that you could also do is if you're really bringing your A game, if you notice you're dividing by a linear factor, you could use synthetic division on that numerator as well to get the quotient. So here we go. So what do I multiply x by to get x squared? It's just going to be regular old x. So then I have x squared and then minus x plus, minus and plus. So this is gone. I get 4x and then bring down that 0, plus 0. And what do I multiply x by to get 4x? So this is going to be plus 4. So we're pretty much done. And minus 4x plus 4. And yeah. Because it'd be minus 4, then you negate it. And so the remainder is 4. Again, we don't worry about the remainder. We just care about this. So our oblique asymptote is going to be y equals the quotient. So y equals x plus 4. That doesn't seem too bad to graph, right? Nice easy slope. Starting at 4. Actually, let's use green. Starting at 4. Up 1 over 1, up 1 over 1. I can draw straight lines with this tool, but you have to have endpoints. So that looks pretty nice. So there you go. I believe that worked. Yeah, that looks great. So those are our two asymptotes. So we have the end behavior model is a line, right? It's a y equals x plus 4. And now they want us to determine if our graph actually crosses our end behavior model. So you could take the simplified and set it equal to the end behavior model. So the simplified function is x times x, x times x plus 3 over x minus 1 equals, and then x plus 4. We're going to set this equal to that to see if they intersect. If you ever want to see if two graphs intersect, you set them equal to each other, right? So there you go. And you'd multiply both sides by x minus 1. So I have, and I'm going to expand the left side. So I have x squared plus 3x equals, then x minus 1 times x plus 4, x squared. I'm going to expand the right side, x squared. So it's going to be plus 4, it's going to be plus 3x, and it's going to be minus 4 equals x squared plus 3x. I'm going to subtract x squared from both sides, and I'm going to subtract 3x from both sides. Because I was going to bring them both together, but they cancel out completely, leaving me with 0 equals negative 4. And we know that that 0 can't equal negative 4. That doesn't make any sense. So that's just an inconsistent scenario. That means ultimately that there is no intersection value between our end behavior model and our actual function. So that's great. If we're on one side of that oblique asymptote, we're going to stay there. We're not going to ever poke through and come out the other side. So then we know it's a good guide for our graph. So I think we're pretty much ready to go here. So they do recommend computing a point between the x-intercepts and the asymptotes. Yeah, I mean, you know, there's a bunch of things going on here that would that we could talk about. But I think we should probably be safest and just plug in some values. But if you want to play with a multiplicity of factors, for example, that could definitely help speed things up a little bit. But we do know that the x-intercepts, for example, the multiplicity of the factors of that numerator are all odd numbers. So we know any time we have an x-intercept, we're crossing. So that's good. So that's something to consider. All right, and then anything else with the asymptote. Sometimes you're up on one side and down on the other, or sometimes you're up on both sides or down on both sides of the vertical asymptote, I mean to say. So it's probably not a bad idea for us to just get a couple test values just to give us a sense for where this graph is. So I would vote that we plot a point at let's test -1. Let's plug in 1, 2, and 3. So I'd like to do f of -1, f of 2, f of 3. F of -1, f of 2, and then f of 3, and then plot those points just so we have a couple extra frames of reference, so to speak. Okay, so the simplified function is going to be, this is f of x is equal to -1 times -1 plus 3 is times 2 over -1 minus 1 over -2. So that's going to just be +1. Let's plot that one. -1, +1. That's very nice. And there's definitely a little bit of a maximum there. We don't know where that is. Don't worry about it. Again, we are just doing a nice sketch. It doesn't have to be perfect. Yes, it does. No, it doesn't really. This is 2 times 2 plus 3 is 5 over 1. So it's just going to be up at 10. So f of 2 is at 10. And f of 3 is going to be 3 times 6 over 2 equals 3 times 3 is 9. So right there. Okay, so now since I have some experience with these, and hopefully you'll have have similar instincts, I know that my graph has to be gravitating towards the asymptote. So the vertical asymptote has a gravity that kind of pulls the graph toward it, and then I'm going to kind of creep away from here, go through these two values, and swing around. And then I get caught in the gravitational field of that oblique asymptote, and then that's just going to pull me off to, I'm really supposed to be getting closer and closer. And actually, when you're graphing these, it's almost fine for you to just don't cross the asymptote, but you can almost graph right on top of it. To the naked eye from far away, it's going to look like you're on top of that asymptote, because the gap between them is like negligible. So I'm going to actually start on the like negative infinity side here, and I'm going to hug this asymptote and slightly try to start to pull away, go up to that hole, keep going, x-intercept, swing around here, come back down, and then you're going to get caught in the gravitational field again of that other vertical asymptote. It's reasonable. And there you go. That should be our final graph. So yeah, step 9, just do what I just did there. And the step 10 is just to check with a graphing utility. All right, you saw my little secret. You can see the other example 3 that's below us. But again, let's see if I can use my magic wand here. And so if you look, the blue graph that's underneath there, that's the Desmos graph, obviously. And you can see, we did pretty well here. Again, I tend to gravitate towards those asymptotes a little too aggressively. It's just exciting. For the most part, I did a pretty good job, though, on that right end behavior. I approached too quickly. But otherwise, yeah. Anyway, I would suggest trying to do similar things on your own. If you have any questions or suggestions, you're by all means, leave a comment. So anyway, good luck, and look forward to seeing you in the future.